The second half of chapter 13. In the second half, we'll start looking at triple integrals, how to write them in different coordinate systems such as rectangular, cylindrical, and spherical. And then we'll talk about the applications in physics with center of mass, moment of inertia. And then finally, we'll look at a general way to change coordinate systems using Jacobians. What I have here is listed our conversions. So in cylindrical, we rewrite it as r dz dr d theta. And then in spherical, rho squared sine phi d rho d theta d phi. These are the formulas you need to know for converting from cylindrical to rectangular, and then from spherical to cylindrical and also to rectangular as well. Let's start by just practicing converting the coordinate systems. So in spherical, I have 5, 2 pi over 3, 3 pi over 4. Just to review how this is written, this is the same as rho, theta, and phi. Rho is the radius from the origin, theta is your angle on the xy plane, and then phi is your angle from the positive z-axis going down. So altogether, if I have theta equal to 2 pi over 3, that would be over here. Phi would be 3 pi over 4, so starting from the positive axis, I'm going to go 3 pi over 4 units down, and then 5 units out. So technically the point is about here. This would be my 5, 2 pi over 3, 3 pi over 4. So if we convert this to cylindrical, we can start with r equal to rho sine phi, which in this case is going to be 5 sine of 3 pi over 4. And therefore it's going to be r equals 5 times square root of 2 over 2. Z is equal to rho cosine phi. So z is going to be 5 times negative square root of 2 over 2, which would be negative 5 square root of 2 over 2. So in cylindrical, the coordinate system would be 5 square root of 2 over 2, 2 pi over 3, and then negative 5 square root of 2 over 2, which is in the format r, theta, and z. So this would be the coordinate system in cylindrical. In rectangular, we also need then our x, which would be r cosine theta. But r we already know is 5 square root of 2 over 2. And then we multiply this by cosine of 2 pi over 3. So altogether this is going to be 5 square root of 2 over 2 times negative 1/2. And so the x-coordinate would be negative 5 square root of 2 over 4. Y is equal to r sine theta, which in this case would be 5 square root of 2 over 2 times sine of 2 pi over 3, which is square root of 3 over 2. So the y-coordinate would be 5 square root of 6 over 4. And therefore in rectangular, the coordinate would be negative 5 square root of 2 over 4, 5 square root of 6 over 4, and then negative 5 square root of 2 over 2. Which kind of matches where the coordinate is, because if you think about it, 2 pi over 3 is back here in the negative x zone, so that would be your negative 5 square root of 2 over 4. Y is obviously positive, so 5 square root of 2 over 4. And then because phi is 2 pi, or phi is 3 pi over 4, z is in the negative zone, so negative 5 square root of 2 over 2. Now, let's practice rewriting an equation in terms of spherical and rectangular and make sure that it makes sense. So I have an equation here. I'm going to go ahead and rewrite it in the form x squared plus y squared minus z squared equals 16, multiplying both sides by 16. And then if I convert to cylindrical, this would be the same as r squared minus z squared equals 16, or r squared over 16 minus z squared over 16 equals 1. So basically what this means is that for any value of theta, I should see a hyperbola oriented along the r direction with a rate distance of 4, and then up and down 4 as well. So if I were to graph just one of these hyperbolas, 4 units out, and then 4 units up, 1, 2, 3, 4, 1, 2, 3, 4, and then that would be where my asymptotes are. So my asymptote would be like one here, and then one here. And then one of the parabolas or hyperbolas would be going this way, and then the other hyperbola would be going this way. And then since this is true for any value of theta, basically I want to think of these hyperbolas as being rotated about the z-axis. So I generate this picture. So if I erase the asymptotes and put those lines back in, you should see the one-sheet hyperboloid that we learned back in chapter 10, which makes sense because if I rewrite this as x squared plus 16 plus y squared over 16 equals 1 plus z squared over 16. Notice as I change the values of z, I'm going to change the radius of my circle and make it larger. So as z increases, I get larger and larger circles, and the same thing as z decreases. So it matches that equation. Now if I change this to spherical, and start from here, this would be rho squared sine squared phi minus rho squared cosine squared phi equals 16. And if I keep simplifying, I'm going to get rho squared, let's make it negative, because then I'll have cosine squared minus sine squared, which would be cosine 2 phi equals 16. And then if I solve for rho squared, let's say, rho squared equals negative 16 secant of 2 phi. Now, normally rho can't be negative, or rho squared can't be negative, but remember, phi itself is between 0 and pi as its possible values. And depending on the value of phi I put in here, I actually could get a negative quantity for secant, and therefore negative times negative, rho squared is going to be positive. For example, if phi equals pi over 2, you get rho squared equals negative 16 times secant of pi. But secant of pi is negative 1, so that would mean rho squared equals 16, or rho equals 4. And by convention, we're going to make sure rho is always positive. So what that means is when phi equals pi over 2, i.e. on the xy plane, my radius is going to be 4. So that would be a circle of radius 4. Let's say it looks like that. Now let's say I use something like phi equals pi over 3. Substituting that in, that would be rho squared equals negative 16 times secant of 2 pi over 3. Secant of 2 pi over 3 is actually negative 2, so that would be 32. So we get rho equals 4 square root of 2. So if phi equals pi over 3, I'm actually at rho equals 4 square root of 2, which would be a little bit larger. So if phi equals pi over 3, I'm going to end up somewhere down here with a little bit of a larger circle. Now, this is not the greatest drawing, so let me try to redraw it again. So when phi equals pi over 3, I should have a circle of radius 4. When phi equals pi over 3, actually that's up here, I'm going to have a circle of radius 4 root 2. Okay. And then notice if phi equals pi over 4, I get rho squared equals negative 16 secant of pi over 2. But secant pi over 2 doesn't exist, and what happens is there is actually no rho value. Now going back to the drawing I have up here of the one-sheet hyperboloid, that makes sense because at phi equals pi over 2, my one-sheet hyperboloid is actually going out to infinity. And now you can see that one-sheet hyperboloid here, if I were to draw it in. So the spherical and the cylindrical match up with the rectangular as a result. Now, let's just try drawing some surfaces in cylindrical and in spherical coordinates. So over here, z equals r squared minus 3 means that any value of theta, I should see a parabola shifted 3 units down. So imagine now I can see a parabola shifted 3 units down. So that would be one parabola. And again, since I can see this for any value of theta, technically that would be my paraboloid equation. So going up here, that makes sense because r squared equals x squared plus y squared. So this would be z equals x squared plus y squared minus 3, which is the equation for our paraboloid from chapter 10. Now if it's in spherical, what you want to do is try to rewrite this in terms of the different spherical equations. For example, if I multiply both sides by rho, I get rho squared equals 3 rho cosine phi. But rho squared is the same as r squared. or I'm sorry, rho squared would be the same as x squared plus y squared plus z squared. 3 rho cosine phi would be the same as 3z. Let me go ahead and convert this to cylindrical. So this would be r squared plus z squared minus 3z equals 0. If I complete the square, I get r squared plus z squared minus 3z plus 9/4 to complete the square equals 9/4, or r squared plus z minus 3/2 squared equals 9/4. So that means at any value of theta, I should see a circle that's 3/2 units up on the z-axis with a radius of 3/2. So what we have generated is a sphere, but not centered at the origin. It's centered at 0, 0, 3/2. Alright, that's enough review of spherical and cylindrical coordinates. So now let's practice actually writing these triple integrals. I have here, I'm going to write an integral to integrate f of x, y, z over the solid defined by x greater than 0, z greater than or equal to 0, y greater than or equal to 3x, and y squared plus z squared greater less than or equal to 9. So let's start with this one here. This would basically be a circle along the yz plane for any x value. So what that generates is a cylinder of radius 3. So I'm going to start by drawing that in. So I have a cylinder of radius 3 moving along the x-axis. Now, I don't want to draw the rest in until I see what shape I need to draw the cylinder over. I have y greater than or equal to 3x. So assuming this is x, y, and z, y equal to 3x would be this line here. X is greater than or equal to 0. So I'm basically starting from this line, going up to the line, y greater than or equal to 3x. Z is greater than 0, so I'm looking at everything above the xy plane, and like I said, inside the cylinder. So if I draw the rest of the shape, it should look something like that. And I'm going to group this together so I can do some different things with it. Okay, so there is my drawing. Now, let's start by going through the different settings for this. Let's start with dz, dx, dy. F of x, y, z, dz, dx, or sorry, I guess it doesn't really matter. We'll do dy, dx. Okay, so these are my inside, which would be from surface to surface. So the lower surface for z is z equals 0, and the upper surface is being defined by the cylinder. So if I solve for z, z equals the square root of 9 minus y squared. So my upper bound for z is square root of 9 minus y squared. Now I've used up all my z variables after I integrate, so the last two can't contain any z variables. In fact, the middle one can only contain x's, because after that I have to work with numbers. So now what you have to do is imagine what happens if you were to project this onto the xy plane, which are my last two variables. So if you project this onto the xy plane, you can kind of see from my drawing that you're going to form a triangle. The triangle is bounded by y equals 3x. This side here is x equals 0. And then this side here is the value for y. So let's see here. Basically, I have to figure out when y squared plus z squared equals 9 and z equals 0 intersect. So that would be at y equals 3. So this line here is y equals 3. So then my bounds for y are from equation to equation, or curve to curve. So that would be from y equals 3x to y equals 3. And then my bounds for x are from x equals 0 to x equals 1. And again, you figure that out because you have y equals 3x. So if y equals 3, then x has to equal 1. So that is the integration if it's dz, dy, dx. Now what I want to do is change the order of integration. So let's take a look at, instead, dy dz dx. So let's see if I can do this. What I want to do is I want to take this graph and I want to rotate it so that my y is going up and down, and it'll be easy to read the top and the bottom. So if I rotate this and I look at it like that, I want to try to figure out where the surfaces is for my y top surface and my bottom surface. So notice here now my top surface is the curve, which is my cylinder. So my top surface here will be, will be coming from the equation y squared plus z squared equals 9. Well, let me write it over here. This would be y squared plus z squared equals 9. But I need it as a y equation, so y is going to equal the square root of 9 minus z squared. So that's my top bound now. Y equals 9 minus z squared. And then the lower surface for this is the plane, which would be y equals 3x. So my lower surface is y equals 3x. So there's my inside one. Notice it's y equals 3x and y equals square root of 9 minus z squared. Now I'm done with my y's, so the only variables I can use are z and x. So if you imagine projecting that onto the zx plane, you're going to see the flat side from the back, but then you're going to see this curve over here. So if I could kind of sketch it here, zx, we're going to see kind of a parabolic curve because of this plane. It's going to look something like this. So basically, I have to figure out what that is going to generate. That curve there is from the intersection of y squared plus z squared equals 9, intersecting with y equals 3x. So if I combine those equations together and get an equation only in terms of z's and x's, that's going to be one of the bounds on my curve. So let's see, y plus 3x, so that would be 9x squared plus z squared equals 9. I need a z equation because it's a dz curve, so z equals square root of 9 minus 9x squared. So now I know z goes from 0 to square root of 9 minus 9x squared. And then my x bounds are from 0 to 1. So there's that one. Let's do one more to get x dy dz. So f of x, y, z. Let's do dx, dy, dz. And let's see if I can get how much of this curve I can get here. So, copy. See if I can get it without the red. Oh, it worked. Okay. So now what I want to do is I want to reorient this so that the x is going up and down, so I can kind of see the top and bottom surfaces on the x. So if I orient it so that x is going up and down, it's not the greatest, but at least you get to see now that the top one is the plane over here, and then the bottom is xy equals 0. So now x goes from 0 to the plane. Now the plane again was y equals 3x, but I can't put y equals 3x in here because it has to be an x equation. So x equals y over 3. So the top bound is y over 3. The bottom surface of this is being defined by the cylinder. Remember, the cylinder was y squared plus z squared equals 9. So now I need 0. I need a y equation. So y equals square root of 9 minus z squared. So this is square root of 9 minus z squared. And then my last one, z, goes from 0 to 3. So there's a way, hopefully, to see each of the different orientations. I will put the original graph back up here so that you have all three of them. And hopefully looking at each of those will make a little bit more sense for those of you that have questions on how to look at the graph in different orientations. Okay, let's keep practicing. So this one I want to do a change of order of integration. I have dy, dz, dx. So if we just kind of sketch out the inequalities for each variable, y is going from 0 to 3 minus z. Y equals 3 minus z would be a plane because it's true for any x value. So I know I have y equals 3 minus z, so I'll start by just drawing in the first one. Z goes from 0 to 3 minus square root of x. So if I solve for this, just so it's easy for me to see, that would mean that root x equals 3 minus z, or x equals 3 minus z squared. So I know I have a parabola shape as well. Let me change the color here. Let's make it blue. So there's my y equals 3 minus z. I need a parabola, x equals 3 minus z squared, so that would look something like this. And then x goes from 0 to 9, which makes sense because if I put in 9 for x, that would be when g is 0. So basically, I'm looking at this, I'm looking at this shape here. So y equals 3 minus x equals 0. And then if I put in the rest of it, it's going to look something like this. So there's my y equals 3 minus x. There's my 3 minus z squared, x equals 3 minus z squared curve, as we saw. Now let's start with dx, dy, dz. F of x, y, z. Okay, dx, surface to surface. So again, what I can do is, I'm going to group this all together. And then this is my x equation right here. So I'm going to rotate this. Oops. I'm going to rotate this so that x is on the top. Okay, so if I rotate this so that x is on the top, notice my top function is the curved surface, and my bottom one is the plane. So that means x is now bounded from the curved surface, which was 3 minus z squared, is the top surface, and then the bottom surface is x equals 0. So if I turn this back around, you should be able to see that looking at it normally as well. Let's see here. So notice back here, x is equal to 0, and then in front, the curved surface 3 minus z squared. Now if I project this onto the yz plane, I should see the triangle, because everything's being covered by the triangle. So we have dx, dy, dz. Y goes from 0 to 3 minus z, and z goes from 0 to 3. So that would be the dx, dy, dz version. Now if I do it dz, dx, dy, it actually looks a little bit differently. If we stare straight down the z-axis, what you're going to see is you're actually going to see two different curves. So imagine this is the x, and this is the y. And if we stare straight down, we're going to see two pieces, like I said. We're going to see, actually it might be easier to do it this way. Let's say this is my positive x right here, and this is my positive y. So if we stare straight down, we're going to see actually this piece right here. So this piece is being defined by the curved surface. And this piece here is being defined by the plane. So the curved surface I'm talking about is this one, and the plane I'm talking about is this one. So consequently, if I do this dz, dx to y, I'm going to have to write it in two pieces. So f of x, y, z, dz, dx, dy, oops, dz, dx, dy. And we'll do another one. F of x, y, z, dz, dx, dy. Now the dividing point for both of these is this curve right here. That curve right there is the intersection of the plane which is z, or the curve, z equals 3 minus root x, or sorry, 3 minus root x, and the plane y equals 3 minus z. So if I intersect those two, I'm going to get y equals 3 minus root x, which is y equals root x. And that actually looks like a curve y equals root x if you rotate it 90 degrees. So now I know which piece to use with which function. Let's say z goes from 0 to the curve, 3 minus root x. That is going to be for this piece here, which would be from y equals 0 to square root of x, and x goes from 0 to 9. Okay. Now if I do the other piece, right here, that part uses the plane, so that would be from 0 to the plane, which is 3 minus y. And that's because that was the plane, let's see, it was originally y equals 3 minus z. So I just rewrote it as z equals 3 minus y. Dx, oh, let's do this, sorry. Let's make this, oh, I guess I could do that. Never mind. So this is dx dy. So actually, I can't use x here, so I have to change this from y equals root x, that one from y equals root x, to x equals y squared. So that would be x equals y squared. And then when x equals 9, y equals 2. So over here, I'm going to do x again from y squared, though, to what value, upper value of x, which is 9, and then y from 0 to 3. Now, let's practice doing it in rectangular, in cylindrical, and in spherical. So here I want to find the volume of a solid that lies above z equals square root of 6x squared plus 6y squared. Square root of 6x squared plus 6y squared would be a cone. And below a sphere of radius 10. So basically this region right here. Let's start with rectangular. So again, to find the volume of a solid, we just put in f of x, y, z equals 1, and then we set up our coordinate system. I'm going to start with dz, and then we'll do dy, and then dx. dz, because we have a very clear upper and lower surface for z, so that's why I'm going to start with that. So if I start with z, the upper surface would be the hemisphere, so that's going to be square root of 10 minus x squared minus y squared. And then the lower surface is the cone, so square root of 6x squared plus 6y squared. Now to figure out the y's and x bounds, I need to figure out what this looks like if I were to project it onto the xy plane. So looking straight down the z-axis, what I'm going to see is a circle defined by the intersection of these two equations. So if I solve for z in the cone, I get z squared equals 6x squared plus 6y squared. So substituting that into the hemisphere, I'm going to get 7x squared plus 7y squared equals 10, or the circle x squared plus y squared equals 10 sevenths. So my bounds for y would be from negative square root of 10 sevenths minus x squared to the positive square root of 10 sevenths minus x squared. And x squared would go from negative, or x would go from negative square root of 10 sevenths to 10 sevenths. So that would be in rectangular. Now let's change it to cylindrical. So in cylindrical, we have r, well, 1 for the integrand, but then I need my conversion factor, which would be r dz dr d theta. Now I need to rewrite these in terms of cylindricals. So x squared plus y squared equals r squared. That means the cone becomes square root of 6r, and the hemisphere becomes square root of 10 minus r squared. Okay. R would be the radius of the circle looking down. So using this equation here, r would go from 0 to square root of 10 sevenths. And then theta is the angle going all the way around, which would be 0 to 2 pi. So there's my cylindrical one. Now let's convert it to spherical. So in spherical, we're going to have 1, again for the integrand. Conversion is rho squared sine phi, d rho, d phi, d theta. Okay. So rho is the radius of this, starting from the origin, going out radially. So it starts from the origin, and then the outer radial surface is the sphere, which has a radius of square root of 10, because x squared plus y squared plus z squared equals 10. It's the same as rho squared equals 10, so rho equals square root of 10. Phi is being defined by the cone, so we need to take our cone equation, which would be 6 square root of 6r equals z, and figure out our phi from that. So that would be square root of 6 rho sine phi equals rho cosine phi. That would mean that tangent phi equals 1 over square root of 6, which means that phi equals the arctangent of 1 over square root of 6. So phi goes from 0 to arctangent of 1 over square root of 6. And then theta goes all the way around, 0 to 2 pi. And there we have it in rectangular, in cylindrical, and in spherical. Now let's try taking a rectangular, figuring out what the graph looks like, and rewrite it in cylindrical and spherical. So again, kind of breaking it up into pieces, what I have to start with is I have z between square root of 3x squared plus 3y squared, and z equals 8. So graphically what I'm looking at is a cone, square root of 3x squared plus 3y squared. So a cone like this. And then z equals 8 would be a plane, so somewhere up here is my plane, z equals 8. I have the equation square root, or negative square root of 4 minus x squared less than or equal to y is less than or equal to square root of 4 minus x squared. That's basically the equation of the circle, x squared plus y squared equals 4. So now I have a circle radius 4 that's sitting actually inside the cone. Notice it doesn't go all the way outside to the cone. And then my last one is x is between 0 and 2. So what that actually means is I'm only looking at half of the circle, the half with the positive x values. So if I were to draw that in, I'm looking at a half circle right here. And that's the volume that I want to try to find. So let's start by doing this in cylindrical. So in cylindrical, we're going to have our square root of x squared plus y squared plus z squared. So in cylindrical, that's going to be r squared plus z squared. Our conversion term r, dz, dr, d theta. So z goes from the cone, that would be square root of 3r, up to z equals 8. Projecting down, I get that circle of radius 2, so r goes from 0 to 2. And theta, since I'm only looking at the positive x values, the positive x values would be these. That would be from negative pi over 2 to pi over 2. And there's our cylindrical. Now, spherical is a little bit different. Let me redraw this picture, and we'll look at it spherically. So here's my plane, but I'm only looking at a semicircle over here. So here's the problem. I'm going to have to use two different values of phi to work this out. Because notice if I were to draw a dotted line right here, these values of phi in here are bounded by the plane z equals 8. But these values of phi over here are bounded by the equation x squared plus y squared equals 4. So I need to figure out the value of phi where those two happen. And the value of phi where those two happen are the intersection of x squared plus y squared equals 4. And, well, actually, I could do this way. I could do this with a triangle. Let's do that instead. So imagine this triangle. R is 2, or R is 2. Z is 8. And so this is the phi that I'm interested in. So tangent of phi equals 2 over 8. So that means for my first integral, I'm going to have the integral this time square root of x squared plus y squared plus z squared is just rho. So this is going to be rho and then rho squared sine phi. And then d rho d phi d theta. For this equation of rho, I'm going to need to use the plane. So z equals 8 is the same thing as rho cosine phi equals 8. So the equation for rho is going to go from 0 to 8 secant phi. And then phi we just determined is from 0 to arc tangent of 1/4. And then theta from the last one we saw was from negative pi over 2 to pi over 2. Now let's do the cone. So for the cone, I have x squared plus y squared equals 4. So I can rewrite that as... Oh no, sorry, for the cone. For the cone, I'm going to use square root of 3r equals z. So square root of 3 rho sine phi equals rho cosine phi. So tangent phi equals 1 over square root of 3. Phi equals pi over 6. So for the second half of my integral here, I'm going to have rho still, rho squared sine phi, d rho d phi d theta. I need to rewrite this in terms of spherical, so that would be r equals 2, rho sine phi equals 2. So rho is going to go from 0 to 2 cosecant phi. Phi is going to go from arc tangent of 1/4 to pi over 6. And theta is going to go from negative pi over 2 to pi over 2. Alright, so then we talked about all the applications with moments and center of mass, and then we talked about inertia, how we had to change it to 3 dimensions. So now the moments are going to be about particular planes, like the xy plane, and the moment of inertia, if I do it about the x-axis, I need the coordinate system in 3 dimensions, so that would be y squared plus z squared for my radius squared now in 3 dimensions. So I'm going to do just one problem so that you see how to set this up. I have a solid with density function 2x cut out of a square, x squared plus y squared plus z equals 4, and the cylinder here. So I'm actually going to, well, I'll leave the cylinder as is. So my sphere of radius 2 is going to look something like this. Say. And then if I were to rewrite this by completing the square, I would have x squared plus y minus 1 squared equals 1. So x, y, z. That's going to be a circle centered at 1, 0 with radius 1, which actually works out really nicely. Because then what I'm basically doing is I have this solid over here that I'm working with. So let's start with the moment about the yz. So moment about yz, triple integral. Moment about yz, the distance would be x. The density would be kx. If we set this up dz, dx, dy, let's say. Upper surface for z would be the top half of the sphere, so square root of 4 minus x squared minus y squared. Lower half of the sphere, negative square root of 4 minus x squared minus y squared. I purposely set dx next because it's easier for me to solve for the x equation, so x would equal plus or minus square root of 2y minus y squared. So bottom here would be negative square root of 2y minus y squared. Top down square root of 2y minus y squared. And then y from 0 to 2. Now, short segue, you can also do this in polar because this equation here, x squared plus y squared equals 2y. Let me write it here. X squared plus y squared equals 2y. We convert it to polar. would be r squared equals 2r sine theta, or r equals 2 sine theta. So if you wanted to set it up in polar, you would have your x, which would be r cosine theta. You'd have your density, which is kx, so that would be kr cosine theta. You'd have your conversion r. dv would be the lower half of the sphere, negative square root of 4 minus r squared, to the top, square root of 4 minus r squared. dr would be bound by the cylinder, so that would be from 0 to 2 sine theta. And then d theta, remember, since this is a circle, not centered at the origin, the period is from 0 to pi. So that was a quick segue. Now, the other thing I said here was the moment of inertia about the x-axis. So inertia about the x-axis. Basically the same setup, except now we're going to use y squared plus z squared for the radius squared, kx for the density. I'm going to go ahead and do this in rectangular so I don't have to convert it to polar. dz dy dx. So then this would be negative square root of 4 minus x squared minus y squared, square root of 4 minus x squared minus y squared. Sorry, I made it dx dy, didn't I? dx dy. Then this would be negative square root of 2y minus y squared, square root of 2y minus y squared, and then y from 0 to 2. So there's an example of the moment and the inertia set up with a three-dimensional object. The last thing I want to talk about in the second half of chapter 13 is Jacobians. So Jacobians basically represent a way to change from one set of variables to another using this matrix as a conversion tool. What I did down here was just kind of show you how it works. So let's say I have x equals r cosine theta, y equals r sine theta from our good old polar days. Then this is a Jacobian, dxy over dr d theta, and it's set up dx dr, dx d theta, dy dr, dy d theta. You do have to solve for the x and y equations. You can't do this in terms of r's and thetas and just reciprocate it. But notice, if I were to set this up, dx dr would be cosine theta, dy dr would be sine theta, and there's my negative r sine theta, r cosine theta for the dx d theta, dy d theta. If I take the determinant, I get that, which simplifies to r, and that's where the conversion dx dy equals r dr d theta comes from. Now I'll just wrap it up with two Jacobian problems so you see how that works. So in this first one, I have this integrand, and they give us the regions, 0, 1, 1, 2, 2, 1, and 1, 0. So I'm going to go ahead and just start by graphing these points. So 0, 1 is right here, 1, 2, 2, 1, and 1, 0. So it looks something like that. This is the first type we talked about, where we have this parallelogram shape, because if you write the equations for each of these lines, this line here is y equals 3 minus x, and actually I want to change this to x, just to make a point. Okay. And then this line here is y equals 1 minus x. This line here is y equals x plus 1. And this line here is y equals x minus 1. So if I rewrite these in terms of x, y expressions, notice I would have, from these two lines here, x plus y between 1 and 3. And from this one and this one, I would have y minus x between negative 1 and 1. So it'd be really nice if I rewrite the variables in terms of x plus y and y minus x. Or I'm going to go ahead and change this so it's prettier. X minus y between negative 1 and 1. So I'm going to define a new coordinate system. I'm going to let u equal x minus y. And that actually serves twofold purpose, because then sine squared x minus y I can rewrite as sine of u. I'm going to let v equal x plus y. And I'm going to rewrite this integral in terms of du's and dv's. So to do that, first of all, I need to figure out my Jacobian. So I need to solve for x and y. So if I add these together, I get x equals u plus v over 2. If I subtract them, I'm going to get v minus u over 2 equals y. So if I set up my Jacobian for this, that would be 1/2 for dx du, 1/2 for dy dv, negative 1/2 for dy du, and 1/2 for dy dv. So that would be 1/4 plus 1/4, which is 1/2. And if that was negative, we would use the positive value because the Jacobian is used to help represent area. So now I'm going to rewrite my integral here. In place of x, I'm going to put in u plus v over 2 sine squared u, and then I'll write dv du. V is the x plus y, so v goes from 1 to 3, and then u goes from negative 1 to 1. Oops, I forgot to put my Jacobian in. So before I write the dv du, let me write in my absolute value of the Jacobian, which is 1/2, and there's my dv du. So v goes from 1 to 3, and u goes from negative 1 to 1. So that would be the setup using the Jacobian. And then lastly, I wanted to wrap it up with one that was not necessarily a parallelogram, and how you pick the u's and v's when it's not a parallelogram. So for this one here, I'm going to go ahead and graph the points. I have 0, 0. I have 2, 1. I have 1, 2. So technically I'm supposed to integrate over this. But this would have to be done in 2 integrals, so I'm going to show the Jacobian and show how I can use specific values for u and v to make this into one variable in terms of the Jacobian. Now, if I try to do something like this, which is typically what we do, let's say I let u equal x minus 3y, since I have an x minus 3y in the equation. Okay. And then if I just randomly let v equal something else, let's say I let v equal x. What I can do is I can basically figure out what the uv coordinates would be if I were to take 0, 0, 2, 1, 1, 2, and rewrite it in terms of u's and v's. So if I took 0, 0, which are my xy coordinates, and plotted them in terms of u's and v's, I would get uv equal to 0, 0. If I took the point 2, 1, and did likewise, I would have 2 minus 3, which would be negative 1, and I would have v equal x, which would be 2. So that's my uv coordinate. And then I took 1, 2, and did the same thing. X minus 3 would be 1 minus 6, which would be negative 5, and v would be 1. And if I graph this, I would have 0, 0, negative 1, 2, negative 5, 1. That region. Which doesn't really help, because I still have to break it up into 2 pieces. So one thing you want to do is kind of look at the coordinates to see if there's anything you can use with the coordinates to help. Notice I have 2, 1, and 1, 2. And if I add both of those up, I get 3. So how about instead, I let u equal x minus 3y still, but I let v equal x plus y. Now what happens is 0, 0 still maps to 0, 0. 2, 1 is going to map to 2 minus 3, which is still negative 1. 2 plus 1 for the v value, which is 3. And then 1, 2 would still map to negative 5 for my new u coordinate, but my v coordinate would be 3. So if I were to graph this, I would have 0, 0, negative 1, 3, and negative 5, 3, where this is my v, this is my u, and now this region here, if I set it up as a du dv, I can do it just in one integral. So just to make sure, this line here would be v equals negative 3x, oops, be negative 3x. And this line here would be v equals, let's see, that would be negative 3/5 x. Or, sorry, u, I suppose. Negative 3/5 u. Alright, so first I got to solve for my Jacobian. So looking at these two equations, if I subtract them, I would get v minus u over 4 equals y. And then if I solve for x, see, I can multiply the second one by 3 and then add them together. So x would equal u plus 3v over 4. So then my Jacobian would be dx du, which would be 1/4, dx dv, 3/4, dy du, negative 1/4, dy dv, 1/4, and that would be 1/16 plus 3/16, which is 4/16. So my conversion term is 1/4. And now, if I set up this, I have x minus 3y, which I said was u. We're going to do this du dv, so first I need my Jacobian, du. So my lower bound for u is this line, so that would be u equals negative 5/3 v. My upper bound for u is this line, so that would be u equals negative 1/3 v. And then dv goes from 0 to 3. And that would be my rewritten equation. That's a negative 5/3. Right. Good luck studying, everyone. Please stop by room 203 if you have any questions.